On January 28, 2026, NASA released an image that rewrote cosmic history. A tiny red smudge, barely visible against the infinite blackness of deep space. To an untrained eye, it looks like nothing. But to astronomers around the world, it represents the most distant object humanity has ever observed. This is MOMZ-14, a galaxy that existed just 280 million years after the Big Bang. Its light has been traveling toward us for 13.53 billion years, and when scientists finally analyzed what that light contained, they found something that made no sense. This galaxy is too bright, too chemically complex, evolving too fast. By every measure of established physics, it should not exist. The researchers who discovered it named their survey Mirage or Miracle. They were testing whether these impossibly ancient galaxies were real or just cosmic illusions. The answer they got has sent shockwaves through the scientific community, because MOMZ-14 is no mirage, it is a miracle. And its existence suggests that everything we thought we knew about the birth of the universe might be fundamentally wrong. So how did the James Webb Space Telescope find something that was supposed to be impossible? What does this discovery reveal about cosmic dawn? And why are astronomers now saying we may need to completely rewrite the textbooks? This is the story of how a $10 billion telescope just broke space history. Again. To understand why MOMZ-14 matters, you first need to understand what the James Webb Space Telescope actually is. Because this is not just an upgraded Hubble, this is an entirely different kind of machine. The Hubble Space Telescope orbits about 540 kilometers above Earth. It primarily sees visible light, the same wavelengths your eyes detect. For 3 decades, Hubble showed us the universe in stunning detail. But Hubble has a fundamental limitation. It cannot see far enough back in time. When we look at distant objects in space, we are literally looking back in time. Light from the sun takes 8 minutes to reach Earth. Light from the nearest star takes 4 years. Light from distant galaxies takes billions of years. So when astronomers want to see the earliest moments of cosmic history, they need to capture light that has been traveling since the universe was young. But here's the problem. That ancient light has been stretched. The universe is expanding. Not galaxies flying apart through space, but space itself stretching like the surface of an inflating balloon. As light travels across billions of light years of expanding space, its wavelength gets stretched too. Ultraviolet light becomes visible light. Visible light becomes infrared. The farther back in time you look, the more the light shifts toward longer wavelengths. This is called cosmological redshift. And at redshift 14.44, where MOMZ-14 sits, the light has been stretched by a factor of 15.44. What left that galaxy as energetic ultraviolet radiation now arrives as infrared light, completely invisible to human eyes, and completely invisible to Hubble. This is why Webb was built. The James Webb Space Telescope does not orbit Earth like Hubble. It sits at a point called L2, the second Lagrange point, 1.5 million kilometers away. At this gravitationally stable location, Webb can keep its back permanently turned to the Sun, Earth, and Moon simultaneously. A sun shield the size of a tennis court blocks all that heat and light. Behind that shield, Webb's instruments operate at negative 233 degrees Celsius. This extreme cold is essential because infrared light is essentially heat radiation. If the telescope itself were warm, its own thermal emissions would drown out the faint whispers from ancient galaxies. And then there is the mirror. Webb's primary mirror spans 6.5 meters across, made of 18 hexagonal segments coated in gold. Gold is not just for show. Gold reflects infrared light with exceptional efficiency. This mirror collects over 6 times more light than Hubble's 2.4-meter mirror. The combination of infrared sensitivity, massive light-gathering power, and extreme cold allows Webb to do something no telescope has ever done before. It can see the first billion years of cosmic history with clarity Hubble could only dream of. But seeing ancient light is only half the challenge. The real breakthrough comes from splitting that light apart. When Webb detected MOMZ-14, it did not just take a picture. It performed spectroscopy. Spectroscopy is essentially reading the fingerprints of light. Every element in the universe absorbs and emits light at specific wavelengths. Hydrogen has its signature pattern. Oxygen has another. nitrogen, carbon, iron. Each element leaves unique marks in the spectrum of light. When astronomers capture the spectrum of a distant galaxy, they can identify exactly which elements are present. And crucially, they can measure how much the entire spectrum has been redshifted. Webb's NER-SPEC instrument, the near-infrared spectrograph, contains a remarkable piece of engineering, a grid of 248,000 individually controllable microshutters, each one the width of a human hair. These shutters can open and close independently, allowing the instrument to capture spectra from over 100 objects simultaneously. For MOEM-Z14, astronomers pointed NER-SPEC at this candidate galaxy for 4.4 hours. What they captured was unmistakable. The spectrum showed a razor-sharp Lyman alpha absorption break. This is the point where all light below a specific wavelength is absorbed by intervening neutral hydrogen between us and the source. The exact wavelength of this break tells you the redshift. But that alone was not enough to confirm the distance. Photometric measurements can sometimes be fooled. A dusty galaxy at redshift 5 might mimic the colors of a pristine galaxy at redshift 14. So the team looked for emission lines, specific wavelengths where atoms in the galaxy were glowing brightly. They found 5 distinct ultraviolet emission lines, including signatures of nitrogen and carbon. Each line independently confirmed the redshift at 14.44. There was no ambiguity, no alternative explanation. MOEM-Z14 is unambiguously ancient and unambiguously real. Rohan Naidu, the MIT astrophysicist who led the research team, described what this meant. With Webb, we are able to see farther than humans ever have before, and it looks nothing like what we predicted, which is both challenging and exciting. Here is where the discovery becomes genuinely shocking. Before Webb launched, astronomers had sophisticated models predicting what the early universe should look like. These models, based on hierarchical structure formation theory, suggested that galaxies beyond redshift 10 would be small, faint, and extraordinarily rare. Finding even a handful would require hundreds of hours of telescope time. Webb has been operating for less than 4 years, and it has already found that bright galaxies at redshifts between 14 and 15 are 182 times more abundant than those models predicted. That is not a small discrepancy. That is the scientific equivalent of predicting you might find one fish in a lake and instead pulling up 182. MOEM-Z14 itself embodies this paradox. It spans roughly 500 light-years across. That makes it about 400 times smaller than our Milky Way galaxy. In terms of stellar mass, it contains approximately 100 million times the mass of our Sun, roughly comparable to the Small Magellanic Cloud, a dwarf galaxy visible from Earth's southern hemisphere. By cosmic standards, this is a tiny object, but it is ferociously active. Analysis of the light reveals that MOEM-Z14's star formation rate surged tenfold in just the last 5 million years before the light we are seeing was emitted. We are witnessing a galaxy in the throes of a violent starburst, forging new stars at a rate that dwarfs anything in our local cosmic neighborhood. And this brings us to the deepest puzzle of all, the nitrogen. When astronomers analyzed the emission lines from MOEM-Z14, they found something that should be impossible. The galaxy shows a highly supersolar nitrogen to carbon ratio. In plain language, there is more nitrogen relative to carbon than exists in our own Sun, far more than standard physics would predict for a galaxy this young. Here is why that is a problem. Nitrogen is not created in the Big Bang. The primordial universe contained only hydrogen, helium, and trace amounts of lithium. Every other element had to be forged inside stars and then distributed into space when those stars died. In conventional stellar physics, nitrogen is produced through something called the CNO cycle inside massive stars. When those stars explode as supernovae, the nitrogen gets scattered into surrounding gas clouds. Future generations of stars form from that enriched gas, and the cycle continues. But this process takes time. Multiple generations of stars need to be born, live their lives, die, and enrich the surrounding medium. At 280 million years after the Big Bang, there simply has not been enough time for this conventional chemical recycling to produce the nitrogen levels detected in MOEM-Z14. So where did the nitrogen come from? The leading hypothesis involves supermassive stars, theoretical stellar behemoths exceeding 1,000 solar masses. that may have formed in the extreme conditions of the very early universe. These hypothetical giants would burn through their fuel incredibly fast and produce enormous amounts of nitrogen before exploding. No telescope has ever directly observed a supermassive star, but their chemical fingerprints may be scattered across the earliest galaxies. And intriguingly, the abundance pattern in MOEMZ14 closely mirrors what astronomers find in ancient globular clusters within our own Milky Way. Naidu made this connection explicit. We can take a page from archaeology and look at these ancient stars in our own galaxy like fossils from the early universe. The nitrogen in MOEMZ14 may be telling us that the first stars were radically different from anything that exists today. Monsters that blazed briefly and died violently, seeding the cosmos with elements that would eventually form planets and perhaps even life. But the mysteries do not stop with nitrogen. MOEMZ14 also delivered a surprise about something called the epoch of Rayonization. This is one of the key transitions in cosmic history and one of Webb's primary science targets. After the Big Bang, the universe was a hot, dense soup of particles. As it expanded and cooled, protons and electrons combined to form neutral hydrogen atoms. This created what astronomers call the cosmic dark ages, a fog of neutral hydrogen that absorbed most light. The first stars eventually ignited and began producing ultraviolet radiation. This radiation gradually ionized the surrounding hydrogen, stripping electrons from atoms and making the universe transparent again. This process is called rayonization. Every theoretical model predicts that at redshift 14.44, the universe should be essentially 100% neutral hydrogen. The first stars should have barely started their work. Rayonization should be just beginning. But MOEMZ14 tells a different story. The galaxy shows no strong Lyman alpha damping ring. This is a specific spectral signature that would appear if MOEMZ14 were surrounded by dense neutral hydrogen. Its absence suggests the galaxy has already carved out a partially ionized bubble in the surrounding fog. This contrasts sharply with the previous distance record holder, JWST 14-0. That galaxy, confirmed in May 2024 at redshift 14.18, does show a strong damping wing. It sits in neutral hydrogen. The two galaxies are separated by only about 10 to 20 million years of cosmic time. They differ by just 0.26 in redshift, yet they occupy completely different environments. This tells astronomers that rayonization was wildly patchy and inhomogeneous. Some regions of the early universe cleared far earlier than models predicted. Other regions remained foggy for much longer. The universe at cosmic dawn was not uniform. It was a patchwork of ionized bubbles and neutral zones. Vivian Wild of the University of St. Andrews, who was not involved in the study, captured the shift in scientific thinking. It was frankly pretty naive of astronomers to have assumed early star formation would mirror later epochs. To appreciate how rapidly our understanding is changing, consider the journey that led to this moment. On July 11, 2022, President Biden unveiled the first deep field image from the James Webb Space Telescope. That single 12.5-hour exposure captured thousands of galaxies that Hubble could never see. The image showed a cluster of galaxies called SMACS 0723, with arcs of light from even more distant objects bent by gravitational lensing. Within weeks, dozens of scientific papers reported unexpectedly bright galaxies at redshifts between 11 and 20. Astronomers were stunned, but they were also cautious. Photometric estimates had been dramatically wrong before. One candidate, called Sears 93316, was initially estimated at redshift 16.7. Follow-up spectroscopy revealed it was actually at redshift 4.9, not ancient at all. The spectroscopic confirmations came carefully and methodically. In December 2022, JADE's GS-Z13-0 was confirmed at redshift 13.2, the most distant spectroscopically confirmed galaxy at that time. In May 2024, JADE's GS-Z14-0 shattered that record at redshift 14.32, a galaxy 290 million years after the Big Bang that was surprisingly bright and already contained significant dust. Now MOEMZ14 pushes another 10 million years deeper into cosmic history. Before Webb began science operations, only one confirmed galaxy existed from the first 500 million years of cosmic history. That was GNZ11, found by Hubble in 2016 at redshift 10.96. Today, GNZ11 does not even rank in the top 13 most distant galaxies known. Webb has completely rewritten the census of the early universe. And MOMZ14 is not the only headline-grabbing discovery in recent months. In January 2026, a Nature cover story finally identified the mysterious little red dots scattered throughout Webb images. These compact reddish sources had puzzled astronomers since Webb's first deep field. The new research concluded they are young, supermassive black holes enshrouded in thick cocoons of gas and dust. A competing team from Harvard proposed an alternative explanation. Perhaps they are instead gigantic, supermassive stars on the verge of collapsing into black holes. Either explanation rewrites our understanding of the early universe. Webb also confirmed the first runaway supermassive black hole, a monster containing 10 million times the mass of our Sun, rocketing through its host galaxy at 2.2 million miles per hour. Behind it trails a wake of star-forming matter stretching 200,000 light-years. The black hole was apparently kicked out by gravitational interactions during a galaxy merger. The most detailed dark matter map ever created was published in Nature Astronomy, using Webb's observations to trace the invisible scaffolding of the cosmic web with twice Hubble's resolution. And a 5-galaxy merger was discovered at just 800 million years after the Big Bang. Far earlier than models predicted such complex gravitational interactions could occur. Each of these discoveries amplifies the same message. The early universe was more active, far more violent, and far more sophisticated than anyone anticipated. So what does the scientific community actually think about all this? Peter Van Dockum of Yale, a co-author on the MOMZ14 paper, captured the emotional significance. First and foremost, at the moment, this is the most distant object known to humanity. That title changes every so often, but I find it is always cause for pause and reflection. He then added something that hints at what might come next. At this point, I would not be surprised if we find galaxies at z equals 15 or z equals 16. Jacob Shen, an MIT postdoctoral researcher on the team, articulated the theoretical stakes more bluntly. There is a growing chasm between theory and observation related to the early universe. But most experts are careful to note that the standard cosmological model, known as lambda CDM, is not necessarily broken. It may simply be incomplete. Rachel Somerville of the Flatiron Institute has argued that these observations can likely be accommodated within the standard framework. Better understanding of bursty star formation, more efficient gas-to-star conversion, and different initial mass functions in the early universe could explain much of what Webb is seeing. The evidence points not to new fundamental physics, but to a cosmos that was far more creative, far more rapidly than anyone imagined. What comes next may be even more extraordinary. NASA has stated explicitly that they expect the MOMZ14 record to be broken again. The original research paper declares it directly. Previously unimaginable redshifts approaching the era of the very first stars no longer seem far away. The Nancy Grace Roman Space Telescope is scheduled to launch in May 2026. This new observatory will survey vastly wider areas of sky than Webb can cover. If galaxies like MOMZ14 are as common as they appear, Roman may find hundreds of them at redshift 15 and beyond. Webb's own theoretical detection limit reaches approximately redshift 20. That corresponds to roughly 180 million years after the Big Bang, the era when the very first stars in the universe ignited. Webb may eventually capture light from the generation of stars that ended the cosmic dark ages. We are not at the end of this story. We are watching the opening chapters of a scientific revolution, written in infrared light that has traveled across 98% of cosmic history to reach a gold-plated mirror floating at the edge of Earth's gravitational embrace. MOMZ14 is not just a record, it is a reckoning. A galaxy the size of a modest star cluster, burning with newborn stars, laced with nitrogen that should not be there, shining from an era when the universe was barely awake. The Mirage or Miracle Survey gave the cosmos a binary choice. The cosmos chose miracle. The discovery deepens three unresolved tensions: why the early universe formed galaxies so efficiently, how nitrogen enrichment occurred so quickly, and why reionization appears far patchier than models predict. For you watching this video, the key takeaway is visceral. We are peering into a time just 280 million years after the birth of everything. And what we see there is a universe already hard at work, building structures with a speed and sophistication that humbles our best theories. The first stars may have ignited only 100 million years before MOAM-Z14 shone. Webb is closing in on them, and when it finds them, or finds something even more unexpected, the story of our cosmic origins will change again. If you found this discovery as mind-blowing as I did, you should check out the video on screen right now. It dives deeper into Webb's other impossible discoveries from the past year. And if you want to stay updated on the next record WeBB inevitably breaks, hit subscribe. I cover space science and the discoveries reshaping our understanding of the universe. I will see you in the next one.